So we'll get started. And then, yeah, won't have class next week. I won't be able to do it. But the week after that, we'll be back to normal. Hopefully I create the event right on Facebook. So that you're all aware. Okay. Recap for what we were talking about last time. Last time we got a good way into regular expressions. Regular expressions look roughly like this thing right here. It's some expression of languages composed of, we have A next to B, it's an implied concatenation there. And then you have union A star. So here's an example of a regular expression. We need to keep in mind that when we see something like A there, or AB there, or A there, then those are representing sets. All the operations happening on them are sets. So always keep that in the back of your mind when you're dealing with a regular expression. If we were to write this out in a super tedious way, this would be equal to, we'd have the set A composed with the set B, union together with the set containing A, and then we'd star the resulting set. And so that, shorthand for that, is just not very readable. And so the theorem we went over last time was proving that if R is a regular expression, then the language it generates is a regular language. So the language generated by a regular expression is a regular language. The next part of what we're going to cover is every regular language can be generated by some regular expression. And so regular expressions are, once again, we're going to prove that they're logically equivalent to NFAs, which are logically equivalent to DFAs. That's ultimately where we're going. And just recap of what we did in this theorem last time. Let's just go over the theorem again really quick. So let R be regex is short for a regular expression. Let R be a regular expression, and observe that there are 6 cases for regular expressions. We had, in our definition of regular expressions, we had 6 possible cases. We had A by itself was a valid regular expression. We had the empty string by itself was a valid regular expression. We had the empty set by itself was a valid regular expression. And then any union, concatenation, or starring of regular expressions are also regular expressions. Right? So for this regular expression, if R is just A, here's the machine that recognizes it. And so A by itself is a regular language, because here's the machine that recognizes it. What about R equal to the empty string? Here's the machine that recognizes it. So the empty string by itself is a regular language. What about the empty set? Well, here's the machine that recognizes it. So the empty set by itself is a regular language. And then we already proved that unions, concatenations, and stars were closed on regular languages. If I take 2 regular languages and I union them together, it's a regular language. If I take a regular language and I star it, it's a regular language. If I take 2 regular languages and I concatenate them together, it's a regular language. So any union, concatenation, or starring of these things is still regular. So what we create, the regular expressions we create are regular languages. And for any regular expression I give you, you should be able to, following the method that we used here, construct the equivalent machine that recognizes it. Right? So there's our recap for what we did last time. So this time we're going to go the converse of this theorem. This theorem says if it's a regular expression, it generates a regular language. Now we're going to prove if it's a regular language, there's a regular expression that generates it. Good? All right. So before we do that, we've got to introduce a new type of machine now called a GNFA, a generalized NFA. And this machine will only be useful for proving the converse of this theorem, and then we're done with this machine after that. So this is the one that we need to know inside and out, like DNFAs or DFAs or NFAs. So it's only useful for this one proof case, and then you can forget that these things kind of exist. All right, so GNFA intuition, here's the intuition for what a GNFA is. It's an NFA where edges are labeled with regular expressions. It's an NFA where the edges are labeled with regular expressions, an NFA with a single except state, and where we have an arrow from every state not including the except state, to every state, not including the start state. So let's make sense of that really quickly. Here's an example of one. Here's a GNFA. So notice that we have an arrow from every state to every state, with the exception of we don't have any arrows to the start state, and with the exception of we don't have any arrows from the except state. Outside of that, pick any two states, they're connected by an arrow. We have an arrow from this state to this state, an arrow from this state to this state, an arrow from this state to this state, and an arrow from this state to this state. Right? And for any NFA, I can quickly convert it to a GNFA. So let me write a random NFA really quick here. If we had some NFA, here's its start state, and it was looking for the substring 0, 0, or the substring 0, 1. Let's make it do that really quick. So here's our start state. We can do an epsilon move over. We can do an epsilon move over. Here's 0, 0. There's our accept. Here's 1, 1. Here's our accept. And then on the accept state, we loop to itself 0, 1, 0, 1. With me so far? NFA that accepts all the strings that contain the substring 0, 0 or 1, 1. Sorry, this can also loop to itself 0, 1. And this can also loop to itself 0, 1. Right? Okay, so how could we convert this into a GNFA? First off, we need to make sure there's only one accept state, not two accept states. So we can fix that really easily by just adding an epsilon transition to a new accept state. So now those aren't accept states. So that's trivial. Right? So now we have one accept state. Now the other thing that we need to do is we need to create arrows from every state to every other state. Now, since this machine can't transition from this state to this state, when I add those arrows, I just add those arrows as empty set arrows. Empty set. And so if I add all the missing arrows with empty set next to it, now the machine is equivalent to what it was before, and now every arrow is a regular expression. Notice that 0 by itself is a regular expression, 1 by itself is a regular expression, empty string by itself is a regular expression, empty set by itself is a regular expression. Make sense? So it's real easy, real trivial to convert any NFA into a GNFA.
Just to remind me, a regular expression.
Three cases. It's a symbol by itself, it's the empty string by itself, it's the empty set by itself.
Right.
And then any unions of these things, concatenations of these things, or starring over these things.
Right, but a regular expression is any expression that is accepted by a regular language. I mean, DEFA?
No. A regular expression was these three symbols, some terminal symbol by itself, the empty string by itself, or the empty set by itself, or any union, concatenation, or starring of these things.
That's the definition.
That was the definition. We had to prove that this was somehow talking about regular languages. That's not given in the definition.
Okay.
And so something like this is a regular expression, because that by itself is, that by itself is, that by itself is. Concatenating those two together then is, unioning those together then is, and starting the whole thing then is.
Those represent languages though, right?
Yeah, to write this out verbosely is like this.
But they could also represent much larger languages, right? Not just the set containing A and the set containing B, but A could represent...
A symbol by itself is always representing the set containing that symbol.
So what I'm wondering is, when you have a regular expression, can you represent larger sets with those symbols, or just that?
Every time you see an A, every time you see a symbol by itself, it represents just a set containing that symbol.
Okay.
It never represents more than that. We don't need to represent more than that. Because with something like that, you could talk about whatever regular language you wanted.
Okay.
I feel like I'm missing your question.
I think so too. I'm wondering, you can have a regular language is just a set, right? It's a set of strings.
A regular language is a set of strings, but so far it has nothing to do with the regular expression.
Okay.
What's a regular expression? You can take a set of symbols, a set containing one symbol.
What has to be one symbol?
Well, no. You can take it containing one symbol, containing the empty string, or you can take the empty set.
But each one of those sets has to have the one thing in it. It can't be a set of multiple elements.
This has one thing in it, this has one thing in it, this has 0 things in it. And now you can take any union of those, so that now allows you to add elements together, any concatenation, and any starring. And when it's all said and done, it's going to be a set. Because they're all set operations.
So when you're writing it out, and you're representing each one of those sets, you can only have one element in each one of those sets. Is that right?
No, no.
I don't think I
Let's
understand.
start writing this out before we start.
Okay.
All right, so A, B. So A by itself is just shorthand for the set containing A. B by itself is shorthand for the set containing B. A by itself, set containing A, right?
So I understand that. What I'm wondering
Now
is,
let's do this really quick. A concatenated with B. What does that set look like?
it is.
So if we were to start simplifying this expression, this is A concatenated with B. That just gives us a string AB. And now we're unioning that with A. So now put A in there. And now we're taking that set and starring it.
Okay.
And now, what does that give us? Well, it's an infinite set. We can't write it all.
Any
But
combination of
gives
those.
us a set containing the empty string. We could do just an A. We could do an AAB. We can do an ABAB. And there's infinitely many things we can do. Okay. That answers it? No?
I understood that.
I'm still asking better question. Notice that this symbol ultimately just represented a single element set.
That's what I'm wondering.
Every symbol always represents a single element set. Okay. Kind of. That's an empty set.
Okay, right. That's the one exception.
Well, still kind of. Because technically, parentheses is a symbol, union's a symbol.
Right.
But these terminal things,
Right.
yeah, the letters, yeah.
Right.
I have to be a little careful with the language. I think you understand me. I just don't think I'm saying it precise enough for it to be technically correct. Okay, anyways, so we start with some NFA, and now we know how to easily convert to GNFA. And that's trivial. Add some new except states, and then for all your missing arrows, just replace them with arrows with the empty string, or with the empty set. And there's a GNFA. Right? Now, we're going to be doing something crucial with these GNFAs, so I want to do one that, so I want to write out processing one for you here. So here's some arbitrary GNFA with 4 states. Notice that each of the labels some regular expression. What we're going to be doing with these GNFAs in our proof is we're going to be ripping out one state at a time until the GNFA is left with just 2 states. And that's the useful thing we're going to be doing with these GNFAs. So let's go over that process really quick. So here's some example of a GNFA. I'm going to rewrite some equivalent GNFA right here, ripping out the state that I drew in a different color here. And so ultimately, all the blue here is going to go away. And we're going to construct this machine over here, which is logically equivalent. I'm going to walk you through the process on how we do that. Okay?
Before you do that, we go over a little more in depth on.
Let's look at a string this thing accepts. That's a good idea. So let's look at a possible string this accepts. So we start over here in the start state. And where could we go? We could go to our accept state just with B. So we accept just a string B. That's a valid string. So here's one of the strings in there. B is one of the strings generated by the scene. But we don't have to do that. We could also go, notice we can't do this move.
Yep. Right.
Right? That's not generating anything. But we could go from here to here, AB star.
Yeah.
So we could also go, let's see, what's a valid string generated by this part of the regular expression? That's, we could do A and then as many B's as we want. B, B, B. So that gets us from here to here.
Or epsilon, right?
Or I could have just done A by itself. Sure.
What I mean is, you don't need any string to transition there, right? Because that's that.
I need at least this if I'm going to go from here to here.
Doesn't that include?
It's A, B star. The star applies to the B.
Oh.
Remember, it's the same way that if you saw 2, 3 squared,
Right.
the squared applies to the 3, not to both. Good question. So yeah, this is AB star, this is not AB star.
If it were that, then you could do an epsilon.
Then you could do an epsilon.
Okay.
So with this one, we have to do an A, and then after the A, we can concatenate on as many B's as we want. So B, B, B. So that was going from this state to this state. Okay, now we're in this state, where do we want to go? We could go back to itself really quick with a AA, and maybe back to itself again with another AA.
Okay.
Now we'll visit down here. Down here, well, we can do that for free with nothing.
Yeah.
A star, we could use just the empty string. I won't bother writing it there. Then while we're down here, maybe stay there with an AB. And then going from here to here, we can do that with B star. Okay, there's some language accepted by this machine.
So in going from that state at the top of your little shape to the accept state, you could also do AB or BA.
Right, I could have also just done an AB, or I could have just done a BA. I could have done one of those, that or that. Both those would have been fine.
That's a union.
Right, union is or,
Okay.
right? This language over here, let's look at what's generated by this. I can do an AB or an A and repeat.
Okay, yeah.
Same thing. Make sense?
Yep.
All right, you want to do another string from this machine, or do you think you're getting it?
I think I'm getting it.
Another?
Sure.
Another string? All right. Start here. Where should I go?
Let's go.
Go up. A with how many B's?
Let's go to
BB. All right, now we're here. Where should we go?
that back down.
Down. With how many A's?
3.
Okay, now where should we go?
Is that an AA and a star?
Yeah, that's AA star. Going back up here. So if we go back here, we have to do an even number of A's. We can do 0, we can do 2, we can do 4.
We could go on nothing.
Or we can go up on nothing. Okay, so we go back up on nothing. Now we're back up here.
You could just do a BA or an AB.
And then we can do an AB or a BA. We'll do a BA. Why not? There's another string accepted by this machine.
Oh, yeah, that's cool.
Good? All right. So now, maybe we'll leave one written up there. And then when we rip it out, we'll show how it goes through this machine.
So only GNFAs.
Actually, probably won't remember that, when we did what transition. So let's do two at the same time when we explain.
You would be able to get to this with just an A, right? Because there's a lot of stars.
Get to this with just an A?
No, you have the
Yes, you could.
Oh.
We go from here to here with just an A, here to here on the empty string, here to here on the empty string.
Yeah.
So yeah, we could get there with just an A.
So,
Okay.
So GFAs and NFAs can't use regular expressions on their edges?
No, they can't have regular expressions on their edges in general. They just have to be things like this.
So what, is there an actual definition for a general NFA?
An actual definition? Yeah.
Okay, so we're doing intuition.
Yeah, we're doing intuition first. Okay, so here's our GNFA, and I'm going to take it and I'm going to convert it into this thing
Okay.
by ripping out the state. And intuitively, the way that we do that, maybe we'll kind of ignore my picture here, we'll just do it ourselves up here. So I have my start state, right?
Yep.
And we're going to have, going to our second state. We can still go to our second state by an AB star, right?
Yes.
So I can still get to my second state with AB star to get to my second state. Now, it's possible that to get to my second state, I could have also come down here and then up there, right?
No.
No.
Well, it just so happens this arrow's labeled, so I couldn't. But it's a coincidence that I can't go from here like that. If this were like a B, then I could.
Yep.
Right?
So
So my point is you have to take into consideration that path. And so technically I could have written out this path. I can also go in going from here to here. I could have also gone down to this and to this. And what's that regular expression?
The empty.
So we'll write it all out. We'll write all of them. So I could have gone from this state to this state directly, which is AB star. Or I could have gone and we could have done the empty set, concatenated with. Once I'm down here, I could do as many ABs as I wanted. So concatenated with AB star. And then transfer back up here with an AA star.
That's cool, yeah.
I could have done that. Now it just so happens that the empty string, or the empty set concatenated with anything is always
Nothing.
the empty set.
Right.
And any set union with the empty set is just that set.
Right.
So it just so happens that this expression simplifies if we did all the algebra. We were essentially adding a zero. We were adding some expression times zero. We were adding zero. We can get rid of all that. And so it just so happens that it's logically equivalent to just that simple.
So really, you're not ripping out states. You're just combining.
I'm getting rid of this state. So I'm trying to say, I'm trying to combine all these regular expressions where I need to make so it's still logically equivalent. So I don't lose anything.
Right.
So that would have been me talking about how I could get from this state to this state, ripping this out. Now it's simplified to this, but I want to write it all that way. So we have that we can go from this state to this state, from this state to this state with just an AB star. Okay, now let's talk about going from this state to this state. That's the except state. How could we go from this state to this state? We could do it with a B,
Or.
yeah, we could have done with a B, or we could have gone on here, we could have done empty set, concatenated with. Once we were here, we could have done as many ABs as we wanted. AB star, and then concatenated with B star is another way that we could have gone there. Just so happens that simplifies to just B.
Would you
So we can replace that with just a B.
put another or if you're going from the AB star to the AB union BA from the start
If I'm going where?
through the AB star and then to the AB union?
No, we're not ripping this state out, so I don't need to worry about any paths that go to that state.
Just for those reasons.
Just for the state that we're ripping out.
Okay, I see.
So I've done the case going from here to here, potentially through here. I've done the case going from here to here, potentially through here. Now I need the case going from here to here, potentially through here.
Wait, one more question to start saying.
Go ahead.
If you could go through the empty set, then would you do?
Including this one?
Oh,
You're
no,
saying?
never mind.
Okay, because we already counted for that.
Okay.
All right, perfect. So now, the last thing we need to keep in mind is how we can go from this state to this state now, right? And we can still do AB union BA. But now we also have the option, in going from this state to this state, of going down here and then over to that state,
Yeah.
right?
Which is.
So going down here then over to that state, we could have done an A star, followed by AB as many times as we wanted. So AB with AB star, and then followed by a B star.
Is there a reason you skip the AA up top?
This one?
Yeah.
Yes. That's how we get from this state to this state. So we still need to include that.
Oh, I see.
So that was how we could get from this state to this state, potentially going through here. We could continue with the same arrow we had before, or we could come down A star, AB as many times as we wanted, and then B star. Right? So finally, the last state that we're missing, we need to do, how could I go from this state to this state using this one? I can't. How could I go from this state to this state using this one? I can't. Okay, how could I go from this state to this state using this one? I could have going from this state to this state, I could do AA, or I could do A star, AB star, AA star, which is what we have written right there.
Wouldn't the first AA be the AA star?
So now I'll get rid of this. No, because in going from this state to this state, I can only do AA once.
Why?
That's how I get from this state to this state. Ignoring the path through here, how do I get from this state to this state? Same way as I did before.
But you can
just
do
AA.
as many times as you want, right?
I can loop back on myself as many times as I want.
That's what I mean.
But how do I get from this state back to this state? AA does it.
Okay, gotcha.
Or I can do A star, AB star,
Oh.
AA star.
Okay.
That's how I get back. Yeah, we're not accounting for every possible loop in the machine. We're just relabeling it. So now, what I had written up here is exactly what we had right there, except for now we have this one filled in. You with me?
Yep.
Okay, so we just barely went from a 4-state GNFA to a 3-state GNFA. And now we're going to go from a 3-state GNFA to a 2-state GNFA by ripping out this middle state now. Right? So if we rip out this middle state, what are all the ways that we can go from here to here? Right?
Right.
Well, we could do B, or we can do AB star. That gets us over here. Then we can do this loop as many times as we want. So I can do AA union A star, concatenated with AB star, concatenated with AA star. This whole thing starred,
Okay.
because I can do that loop as many times as I want. And then continue on to this part. Then I can continue on to AB or BA or A star with AB star, B star. And that's the other way I can get there. And so we ripped out that state.
Okay.
And now notice what we're left with. A machine that only has 2 states and 1 regular expression. And now notice a string can only get from the start state to the accept state if this regular expression generates it. So we can take some NFA, convert it to a logically equivalent GNFA, and then we can keep ripping states out of that GNFA until it's down to 2 states. And we have something logically equivalent, which is just basically a regular expression.
So really the only difference between an NFA and a GNFA is an NFA can't have regular expressions on its edges while a GNFA can't.
Right. And remember that with the GNFA, we have an arrow from every state to every state with the exception of the start and end state. And the GNFA only has 1 accept state. And we need the GNFA to have only 1 accept state. That way when we get it down to a 2-state machine, we're done. Okay, so there's an example of ripping states out of the machine, so hopefully when we talk about it in the proof it makes sense to you. Here's a general idea. For any 2 states in my GNFA, Q sub I and Q sub j, and then some other state I want to rip out that you can get from Q sub I to Q sub j through, here's a picture before. In ripping out this state, then our transition from Q sub I to Q sub j changes from just R4 to, we could have done R1, and then R2 as many times as we wanted, and then R3. So we can do R1, R2 star, R3, or we can just do R4, where R1, R2, R3, R4 are just whatever the regular expressions are that those labels are labeled with. So in general, you have a process like this, and you convert to this, and that's what we did over and over again. Here's an example right here. This AB star is the same thing as R1. This part right here is R2. This part right here was R3. And this part right here was R4. So when we had this, which is the same as this picture, and we ripped out that state, it turned it into this. It turned it into R1 concatenated with R2 star concatenated with R3 union R4. Make sense? And so in general, that's what we do to rip out states. Goes from that to that for every possible path through it. For every Q sub I and Q sub j that take a path through our rip state. So we applied this procedure a couple times in going from here to here. We applied it to these two states when we wanted to rip out that one. We applied it to these two states when we wanted to rip out that one. We applied it to these two states when we wanted to rip out that one. And it just was real easy since we put an empty symbol there to keep it nice. So two of the expressions simplified to just one term. Make sense? Okay, so there's our general procedure. Now let's give a definition and then jump into our final proof. So, definition. Let R be the set of all possible regular expressions you could come up with over the input alphabet sigma. So if sigma is just 0, 1, then R here represents a set of all possible regular expressions you could have with zeros and ones.
So any combination possible.
Any combination possible. Obviously, there's infinitely many. Okay. Then, a GNFA is a 5-tuple, G equal to our set of states, our input alphabet, our transition function, our start state, our accept state. Remember, we only have one accept state with a GNFA. Where Q is the states, sigma is the alphabet, Q naught is the start state, Q accept is the accept state, and our transition function. Our transition function, you give it two states and it spits out the regular expression connecting those two states. So for my input function, if I would have plugged in this state and this state, then it would spit out the regular expression AB union BA. If I would have put in this state and this state, it would have spit out the regular expression AA. If I put in this state and this state, it would have spit out the regular expression empty set. So our transition function, you give it two states, it takes two states, and it spits out a regular expression. Now, exceptions on the two states you can give it. This is the state you're coming from, this is the state you're going to. So notice that we can come from any state except the accept state, and we can go to any state except the start state. That's why we minus those from our states in each of these. So you can never come from the accept state, and you can never go to the start state in a GNFA.
So just to remind me, in a normal NFA or DFA, you have a state crossed with the alphabet, right?
To get to the next state.
And this, you're crossing two states to get. So it's kind of switched.
It takes two states and it spits out a regular expression.
So the edge is the output instead of the...
Yes, this outputs the edge label rather than which state to go to.
Okay, so there is
That's
a
correct.
slight...
There is a difference. So how it accepts is a little bit different.
Right.
So, to make it very clear, I think I'm supposed to label over here. If we call this one Q naught, and we call this one Q1, then our delta function on Q naught Q1 is equal to AB star. On Q1 Q1, it's equal to AA. Alright, so now when does a GNFA accept? You already have intuition for it when the regular expression can create the string. Let's generate a string really quick one more time here so I can label the parts and you can see them in the proof. So using this machine one more time, we'll go from Q naught to Q1 to, we'll just go straight to Q accept. We'll keep it nice and short. Q accept. And going from Q naught to Q1, we're going to generate the string A, B, B, B. So this right here is going to be W1 in our proof. And then in going from Q1 to Q2, we're going to generate the string AB. So this will be W2 in our proof. And our string will only be split into two pieces. The part that was generated from the first regular expression and the part that was generated from the second regular expression. So a GNFA accepts some string W, broken up into pieces W1, W2, all the way through WK. In our case, we just broke it up into two pieces, because it was only generated by two of the regular expressions here. So it accepts that string, where each WI is some string you can create with the language. In our case, it was some string of A's and B's, right? So where each of those little pieces can be some string of A's and B's or zeros and ones or whatever your language is, provided that there exists some sequence of states, R0, R1, R2, RK. In our case, we had Q1, Q0, Q1, Q accept. So, sorry, we're also going to be calling those R0, R1, R2. And in our case, R0 was Q0, R1 was Q1, R2 was Q accept. So if there exists some sequence of states such that R0 is equal to the start state, which in our case it was, R0 was Q0, and our last state in our sequence is the accept state, which R2 in our case is the accept state, and where each W sub I, each piece of the string, that piece and that piece, each piece of the string is in the language generated by that portion, or that regular expression. So generated by R sub I, where R sub I is the regular expression going from the previous state to the next state for each I between 1 and k. So W sub 1 has to be generated by the regular expression between these two states, or that regular expression. W sub 2 has to be generated by the regular expression between those two states, or that regular expression. So that's what this is saying. Each piece of the string is generated by the corresponding regular expression. The regular expression that you get in going from the previous state to the next state.
So why is there a star?
This is supposed to be, sorry, this is an I minus 1 and I minus 1, I. And we do that for all the i's between 1 and k, where k is this number, in our case 2 right there.
So why is there a star above the alphabet symbol?
Right there?
Yeah.
For wi is not one symbol. So W sub 1 is not one symbol. It's a string. So in our case, what's our input alphabet over here? It's just AB. Our alphabet
Okay.
is just AB.
Yeah.
So AB star is just some string of ABs. So star is just a string of ABs. Is that a string of ABs? Is that a string of ABs? Would you know what to do with it if it wasn't a string of ABs?
I see what you're saying.
Right, so we just need to make sure that these are things from our input language. In other words, you don't need to go and try running the string 219 square on this machine because it's not in its language. So that's all this requirement is making sure of. Okay? So it's exactly what you expect. When do we accept a string? When each of its individual components can be generated by the corresponding regular expression. When the first part can be generated by that one, and when the second part can be generated by that one, or we could have come up with some longer path. So that definition for when it accepts makes sense? Okay, then now we're ready for the theorem to finish the section. If A is a regular language, then some regular expression generates it. So, sorry, I didn't say let A be regular, but let A be a regular language and let N be the NFA recognizing A. So if A is a regular language, there has to be some NFA that recognizes it.
Before we do this,
Go ahead.
would you mind giving a concrete example, like a specific example of A being a regular language and the expression that generates it?
Pick it. Here you go.
So what is?
What's the language it generates? The same language this machine accepts.
Okay. Just getting a little bit of abstract. That's all.
It's all very abstract. Yes, this is a very abstract course. Okay, so we're proving that if A is any regular language, pick any regular language out of the blue. If it's a regular language, I should be able to come up with a regular expression that generates that language. That's my proving I should be able to do. I'm not telling you how to do that, I'm just proving it's possible to do that. Make sense? Now if a language is regular, what do we know about the language?
That it can be made into an NFA or DFA.
That some NFA or some DFA has to accept it.
Yeah.
So if I know that A is a regular language, there has to be some NFA in existence. I have no clue what it looks like, but there has to be some NFA, call it N, that recognizes A. Right? Now, we can convert N, our NFA, to a GFA by restricting it to only have one accept state and then adding all the empty arrows that we need. To a GNFA. So let M be the NFA recognizing A, and let G be the GNFA generated by adding a new start/accept state and any necessary empty transition arrows. Right? Okay. Then we can convert N to a GNFA by adding new start and end state and empty. I think I kind of repeat myself twice. We can also add empty string arrows and empty state arrows. Empty string was like when we added a new accept state, we had to epsilon over here. Okay, so we can go from an NFA to a GNFA. Now then, well, let K be the number of states in G. If this is G, K is 4. If this is G, K is 3. If this is G, K is 2. So let K be the number of states in G. If K is equal to 2, if G only has 2 states, then G only has a single transition, call it R. It's like the case right here. G has a single transition, R, and so the language of R and the language of G are the same thing. This machine right here, the language of R and the language of G are the same thing.
What is a language? Is it a string?
All the strings it generates.
Yeah, so it's a string.
It's the set of all the strings it
Set of
generates.
strings.
Then it accepts. Right?
Yeah, that it accepts.
Okay.
So if this regular expression right here generates a string, this machine accepts it, by definition.
Okay.
So if our GNFA has 2 states, then it can only have a single regular expression, and so the language of the regular expression and the language of the machine are one and the same. Right?
Yep.
Then, if k is more than 2, randomly pick some state inside of Q, we'll call it Q sub rep, randomly pick some state, doesn't matter which one, as long as you don't pick the start state or the accept state. So randomly pick some state in Q that's not the start state or the accept state. So we're looking at this machine, we're going to randomly pick one, that's not the start or the accept, so we can only pick one of those two. Pick one, we're going to call it Q sub rep. And let G prime equal, we're going to construct a new machine now, G prime. The states of G prime are going to be Q minus Q sub rep. We're going to get rid of that state. We're going to come up with a new transition function, delta prime. We'll have the same input alphabet, sigma. We'll have the same start state, Q sub naught. We'll have the same accept state, Q sub accept. So the only difference between G and G prime is we lost one state and we're going to have to modify our transition functions on it. So G prime is equal to this new machine that where for each Q sub I in our new states, for each Q sub I that's not an accept state, and each Q sub j that's not a start state, because we're going to be talking about going from Q sub I to Q sub j. So Q sub I is all the states that we can go from. Q sub j is all the states that we can go to. Notice I'm talking about this picture over here. Q sub I is a state we can go from, Q sub j is a state we can go to. So what I'm guaranteeing in this picture is that whatever Q sub I is, it's not the accept state, and whatever Q sub j is, it's not the start state. So Q sub I is any state that's not the accept state, and Q sub j is any state that's not the, I said that backwards. Q sub I is any state that's not the accept state, Q sub j is any state that's not the start state, and we defined our new transition function, delta prime, from Q sub I to Q sub j to be R1 concatenated with R2 star concatenated with R3 union R4. Exactly like we said there. Where R1, R2, R3, R4 are the same as I said in the picture here. Where R1 is a transition from that to that, R2 from that to itself, R3 from that to that, R4 from that to that.
Is that not a specific case though? That's not.
We're going to do this for every Q sub I and Q sub j.
Oh, okay.
Right? So when we were talking about ripping out this state here, we have to go through all the possible Q sub i's and Q sub j's. So Q sub I and j could first be these two states, then they could be these two states, then they could be these two states. And those were all the cases we had to handle.
So why is it saying that they can't be the except or?
Q sub I can never be the except state. Q sub j can never be the start state.
I see it, yeah. Okay.
Because otherwise you'd have an arrow going from the except to the start, which can't happen. So Q sub I is any state that's not the except state. Q sub j is any state that's not the start state. And for any combination of states you can get like that, we're going to redefine our transition function like this. So rather than this transition, we now have this one. Good? Okay. So then, the language of G sub prime is the same as the language of G. We have a logically equivalent machine. And so we can just relabel G sub prime G. So whatever machine we have in the end, let's call that our new G, and we repeat steps 4 through 6. What does 4 say? If we're down to 2 states, we're good. If we have more than 2 states, rip another one out. Go back to 4. If we have 2 states, we're good. If we have more than 2 states, rip another one out. It's a finite state machine, so this can only happen a finite number of times before we're down to 2 states. And once we're down to 2 states, we're good. So eventually condition 4 will be met. Therefore, there exists some regular expression R such that the language of R is equal to A. In short, if A is a regular language, we can create an NFA that recognizes it. Every NFA can be converted to a GNFA. Every GNFA can be reduced to the point where it only has 2 states. Once it only has 2 states, there's a logically equivalent regular expression to that GNFA.
Okay.
That's what we did in the proof.
Does that mean that any GNFA can also be reduced to a DFA?
No.
But that's only for NFAs, right?
Every DFA could be
Can be converted to a GNFA.
with some exceptions. Here's roughly the picture.
Right. But any NFA can be converted.
Any DFA is an NFA, and any NFA is a GNFA. So any DFA can be a GNFA.
Right.
You can't just say the reverse.
But
It happens to be true that we could construct a logically equivalent DFA for a GNFA, but we don't want to give some procedure to do that. Going from this to this to this, that's real easy to do. And we can give real simple rules on how to do it.
but the 2 inner circles are logically equivalent, right?
Well, now we know all 3 of these circles are logically equivalent. We just showed explicitly that we can get from here to here, and that we can get from here to here. We gave procedures on how we can do those things.
But we also showed that you can get from an NFA to a DFA. Right? Can we not do that?
For an NFA to a DFA, or
Yeah, you said you could.
They're logically equivalent.
yeah, we did show. I'm trying to remember how exactly we showed it though.
We did that proof.
You just make it big and big. Understand?
Oh yeah. Now I remember with the power set. Yeah,
But you can't necessarily go from
but for free. Let's say coming out the door, I throw some machine on the board. If the machine I throw on the board is a DFA, it's automatically already an NFA, and it's almost automatically already a GNFA.
Right.
If I throw a GNFA on the board, it is not almost automatically a DFA.
Oh, I
Or
see
an
what
NFA.
you're saying, yeah.
So that's what I was wondering. A GNFA cannot necessarily be converted to an NFA.
Yes, it can. In terms of computation power, these are all 3 logically equivalent, and I can convert one machine to the other.
Oh, so GNFA.
I'm saying draw a machine on the board. If the machine you drew is a DFA, it's already an NFA, and it's already a GNFA.
Right.
Or draw some machine on the board. If it's already an NFA, it's already a GNFA. It's not necessarily already a DFA, and you'd have to work with it.
But you can make it that way.
But you could, by working with it, make it that way.
So you can.
And it would be a long, tedious process, but you could.
can theoretically make any GNFA a DFA.
Yes, they're all 3 logically equivalent.
Okay.
Talk about the exact same languages. Yes. Good. Anything else with those?
Is this a pattern that we see with all GFAs is the R2 squared, not squared, starred with the R1?
We literally just use GNFAs for this proof right here, and then
Do they have
we
no
won't see
other
them again.
purpose? It seems like they could be used.
Well, you can always find use cases for things. And I wouldn't dare say, no, it's not useful for anything else. We just won't care about it anymore.
So how would you show a star in a DFA? If it can't do like epsilon to make it go which ways?
A loop.
You have to make, yeah.
A DFA can have a loop.
That means at the end you have to say you can't go this place and this place. You can't do that in DFAs. Otherwise it's just one loop. What if you're doing like AA and then AB and then except?
So let's do really simple. Something like, you're saying something like 0, 1, star, right?
With like a 0, 1 at the end.
It's still the same thing. I guess technically you're requiring there to be at least one. Okay.
Okay, now create DFA.
Okay, so let's create the DFA that recognizes this thing. So it has to have at least one 0, 1, but then it can have as many as we want. Right? So here's our start state. Once I've seen a 0, go over here. Once I've seen a 1, go over here. Right?
Those should be at the end, right?
Then, if I see another 0, I go over here. Here's my except state, sorry. If I see a 0, go over here. Read a 0, read a 1. We're good. Oh, you want another 0? Then you have to have another 1. Okay, you're good. Oh, you want another 0? Then you have to have another 1. You're good.
So you're just saying that that star is always nothing?
That star means I have to have a loop somewhere.
Okay.
That's what the star means.
Oh, I see what you're kind of saying. What if you switch that 0, 1 at the end to a 1, 0?
To a 1, 0. That would just mean I need to require a 1, 0 first, and then I can have a 0, 1.
Why?
Once I have a 0, I need a 1. It's just not going to loop back on itself.
Why are you ignoring the
Okay. You want 1, 0. So we want 1 there, 0 there, and then 0, 1 star, right? So this comes away on a 0 to this state, and then back over on a 1.
So doesn't that have to
So
start with
1, 0. Oh, we need that one first. Sorry.
Yeah, what's, yeah.
So we want the loop first. So the loop first is, we start out here, and we could go to our 1, 0 if we want. Or we could come down here on a 0,
But that's not a DFA's word.
and then a 1.
Oh, it's not. Okay.
So I can do 0, 1, 0, 1, 1, 0. And then any arrows I don't have there, I could just have them go to some dead state that we never escape to get all my missing arrows. So this one on a 0 just comes to this dead state. This one on a 1 comes to dead state. This one on a 0 or a 1 comes to dead state, and this loops to itself. 0, 1. If we wanted to write everything out. Typically we don't bother filling out the dead state.
We have a state that has your top left state there goes to 2 places on 0.
Oh, thank you. Yep, should have that there. Good catch. And this one on a 0 is where I meant to put that. It should go there. Right?
Right.
And we can do it for anything you came up with. Pretty confident after proving it. Alright. So now, unless you have any more questions about regular expressions, we're done with them.
So why do we study regular expressions?
They're used a lot in computer science. They're very useful.
Can you give an example?
It's like you're saying, why do we study algebra? Because it's used a lot in the real world. Why is algebra the field we study rather than these other fields? It's used more.
Well, it makes sense that algebra can be represented in a lot of real world situations.
Well, obviously, regular expressions aren't near as generalized as algebra.
Right.
But why algebra over the other fields of math? It's one that shows up a lot. So why not? Why regular expressions is logically equivalent? Because they show up a lot.
Okay.
And they're easy to work with. Relatively speaking, those symbols, it's real easy for, once you get comfortable with them, it's real easy to understand the language that something like this is talking about, like he just said. We instantly knew what that language was. And so it's a very nice way of representing languages. Real easy to talk about. And I said we won't bother with regular expressions again. That's really not true. We'll still see regular expressions come up. And they'll be the easiest way to do quick filters. And that's what they're good for. And you'll understand what I mean when we get to Turing machines. Because we'll use regular expressions all the time as quick filters. To really quick get rid of all the languages, all the strings we don't want to talk about. And then the ones that we do want to talk about will always be like a subset of a regular language. And a regular expression can really quick give us the language we want to take a subset of.
That makes kind of sense.
Yeah, that's what they're used for, filtering, basically.
That makes more sense.
Even in programming. Okay, so now we're going to move on to talking about non-regular languages. So far, everything we've been talking about is a regular language. Now we're going to talk about non-regular language. We've already briefly talked about an example of a non-regular language. 0 to the n, 1 to the n, I told you that is not a regular language. It is not possible for you to create a DFA that can recognize all the strings that has an equal number of zeros, or some number of zeros followed by an equal number of ones. You can't build a machine to do it. Right? We're going to quickly talk about how we proved, not really proved, but talked through how you could prove that recognizing this language is impossible. And the way we did that is we said, some hypothetical situation. I asked Levi went home, he built the machine. I asked him first, how many states were in your machine? And he said something like, P equal to 20, there were 20 states in my machine. And so I said, okay, consider the string s equal to 0 to the 20, 1 to the 20. Now, if his machine has 20 states, then let's say it this way. If you read 20 input symbols, how many states do you have to transition through?
19?
No, 21.
21.
Think about,
Because you have to start.
yeah, really simple. If I'm in this state and I read a 0 and I go to this state, to read one symbol I have to go through 2 states. If I then read a 1 and go to this state, I touch 3 states by the time I read 2 symbols. And then if I'm on 0, we come back over here. Okay, I've touched a 4th state, or a 3rd state, reading 4 symbols, if I were keeping track of my sequence of states. So if I was keeping track of the sequence of states I went through, by the time I go through 20 input symbols, I had to go through 21 states. Maybe repeating, maybe not.
So P is 21?
No, P is 20.
Okay.
So P was the number of states in your machine.
Not the number of transitions.
Yeah, P is the number of states in your machine. So I say consider this string s equal to 0 to the 20, 1 to the 20. In reading the first 0 to the 20 input symbols, if we were to keep track of every state that you were in, you would have transitioned through 21 states. There's only 20 states in your machine. You have to go through 21 states just to read the zeros, which means in just reading the zeros, you have a loop in your machine somewhere. So whatever your machine does, starts out here, we were in this state, we moved over to this state, we moved over, dot, 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 dot. We move over to this state. Eventually, there has to be some loop of states that takes you back where you started. And then finally, you went along, and ultimately, dot, 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 came to some accepting. There has to be some loop in the machine. Right? And so what we do then is I ask Levi, okay, how many zeros did you see before we got to our first loop? Before we got to the loop, before we get to this state? How many zeros do you see? And he tells me something like 10. So if I do 0 10 times, then that gets me from here, sorry, let's do another. Here's my start state, we're going along, da da da. Eventually, after reading 10 zeros, we're here, right? Then I ask Levi, how many zeros did you read in transitioning to get back to this state in your loop? And he tells me something like there were 5 zeros in that case. Right? And then he went on reading his other 5 zeros, who cares, and then his 21s. So here's a string rebroken up. Sorry, let me write to the side. Let's write under here. So we have 0 to the 10, then 0 to the 5, then 0 to the 5, 1 to the 20. Here's his input string. This piece right here, where all the symbols that came before the loop, we'll label that with an X. These symbols right here were all the symbols that were in a loop. We'll call that Y. And here's all the symbols that came after the loop. These might be looping again, maybe not, maybe they are, we don't care. The point is, this y part was definitely in a loop. So then, if we do the y part twice, that should still be a string in his language. It should be perfectly valid to go along here, do the loop, go along here, and do the loop again. As long as we loop the same way. So it should be possible to do x, y 2 times, and then z. And if we do x, y twice, and then z, then that string is s equal to 0 to the 25, 1 to the 20. Right? And is 0 to the 25, 1 to the 20 in this language? No. So we just barely proved that his machine, we outlined the big idea for how we might do a proof, that his machine is accepting strings that it shouldn't. So he did not build a machine that recognizes this language.
What if you put 5 ones in the loop too?
You could, but that's not the point.
The loop had to come in just the zeros. Had to. In just reading the zeros, we had to go through 21 states. There's only 20 states in the machine. And that's why it works. So I had to be a little bit clever in how I argued with Levi. And I had to make sure that in my argument I made it clear that the loop happened over here. Because if I would have said, Levi, consider the string 0 to the 10, 1 to the 10, then yeah, now maybe the loop is zeros and ones, and maybe running the loop again happens to still give a string in the language. I need to be clever and come up with a string that you for sure could have pumped up this way and add more zeros to. And so we specifically chose 1 to 20, or 0 to 20, 1 to 20, so that the loop had to happen in the zeros. You see the idea? Okay. So that gives you an idea of how we prove a language is not regular. Now we'll go over exactly what we mean by the pumping lemma, and that's what we'll actually use to prove that languages aren't regular. First, a little bit of logic. True.gov. Well, let me say something here a little bit differently now. The fact that we were able to find a string long enough that forced the machine to have a loop meant that we could make the machine loop as many times as we wanted. We call that pumping up the string. And so the pumping lemma is in short going to say, if you have a regular language that contains really long strings, strings much longer than the number of states in your machine, then there has to be ways to pump that string up and have it still be in your language. That's ultimately what the pumping lemma is going to say. And that's why it's called the pumping lemma. You can pump it up. You can run it through the loop as many times as you want. Long strings have to loop. We can loop it as many times as we want, and it should still be a valid string in the language. That's why it's called pumping lemma. Anyways, so a little bit of logic. Alpha implies beta, logically equivalent to not beta implies not alpha. If Donnie's wearing shoes, then Donnie's wearing socks is logically equivalent to if I'm not wearing socks, then I'm not wearing shoes. This to this is called the contrapositive. That is also how we're going to be using the pumping lemma. So a little bit weird. So first, what are we going to prove? We're going to prove something called the pumping lemma, which says if you have a regular language, then it has a pumping property. Long strings can be pumped up this way on a loop. We're going to be using it in our proofs for the contrapositive. We're going to prove that some language does not have the pumping property, and therefore it is not a regular language. I think I said that a little weird, so let me say it again. We're going to prove something called the pumping lemma, which says if you have a regular language, then it has a pumping property. It can be pumped up.
Is that a fact, or is that just something?
That's something that we're going to prove. It's a fact. Regular languages can be pumped up. They have this pumping property.
Every language.
And we'll,
regular language.
every regular language. And we'll prove that. And that's called the pumping lemma. This implies this is called the pumping lemma. That's what we're going to prove. When we go to actually use the pumping lemma, we use it this way.
Okay.
We use the pumping lemma to show that a language isn't regular. So I'm going to take some language, I'm going to show you can't pump it up, because then you get something that's not in language, and therefore it's not a regular language. So I'm going to prove regular languages implies it has a pumping property. When we go to use it, I'm going to show some language does not have the pumping property, and therefore said language is not a regular language. And so this section, non-regular languages, is about proving languages are not regular. Make sense? Big picture? Okay. Now let's try and eat this pumping property. Because here it is.
Yeah.
It's a beast. Gotta wrap your head around it. If A is a regular language, then there exists some natural number, we call it P, the pumping length. It's going to be the number of states in the machine. The same thing I had P up here. There's going to exist some pumping length, such that for any string in the language longer than that pumping length, it has to have a loop. That's what we're going to be saying next, but I'm just trying to help you consume it piece by piece what we're saying. Take the number of states in there. If you have strings that are as big as the number of states or bigger, we're going to have to loop. Okay, so.
As big?
As big or bigger. Yes. If.
Oh, yes, I get that.
Perfect. If you're going to read 20 symbols, you have to go through 21 states.
Yeah.
Right. So there exists some P, some natural number, we call it the pumping length, such that for any string in the language longer than the pumping length, as long or longer than the pumping length, there exists X, Y, and Z. There exists some way we can rewrite the string S as X, Y, and Z. We can break it up, same way I broke it up here, X, Y, Z. There exists some way of breaking the string up into components X, Y, and Z, such that the X, Y part, this first part, is less than or equal to the pumping length. In other words, the X, Y part contains the loop. The pumping length is the length in which we're guaranteed there's a loop. That's intuitively what it is. Levi told me his machine has 20 states, so I know I'm reading the first 20 symbols, there has to be a loop. So I set up my machine, I picked it so that X, Y here, the part that includes the loop, Y is going to be the loop, X is the part before the loop. So going up to the end of the loop has to be less than the pumping length, getting back to where you started, the repeat in the state. Okay, so if your language is regular, then there must exist some P, the pumping length, such that for any string as long or longer than the pumping length, you can break it up into components X, Y, and Z, such that the XY part is less than the pumping length. The Y part, the actual looping part, is at least 1, because the smallest loop you can have is it goes to itself. And so that still reads one symbol. Such that for any natural number, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever, for any natural number, X, Y to that natural number, Z, is still in the language. In other words, you can take the loop as many times as you want. You could have never taken the loop, which is taking it 0 times. You could have taken the loop 1,000 times, and it's still better be in the language. If your machine contains a loop, here's another way to say it. If your machine has P states, and it's reading a string that's going to have to go through more than P states, then it's going to have to loop somewhere in a loop bigger than 1. And no matter how many times we let it take the loop, it's still going to be something in the language, something the machine still recognizes.
Okay.
Yeah, 4 quantifiers is a pain to swallow.
Oh, we're not even proving it.
No, this isn't the proof. This is understanding what we're trying to prove.
Is equal S supposed to be such that?
No. There exists X, Y, and Z equal to S. So X, Y, and Z is just rewriting S.
Equal to the string.
So S here was 0 to 21 to 20. I rewrote it as X, Y, and Z, 0 to 5, or 0 to 10, 0 to 5, 0 to 5, 1 to 20. Intuitively, X is what comes before your loop, Y is what for sure loops, maybe you had other loops, but Y for sure loops, and then Z is whatever comes after.
Okay. So it's X up to your first loop?
Yep, X is everything up to your first loop, Y is the actual loop, Z is everything that comes after,
Okay.
in your input string.
Don't you want X, Y to be greater? Or equal to p.
No, it's less than or equal to p.
Isn't
Which means that your loop, y, has to come within the first p symbols. Levi told me his machine had 20 states, so I was guaranteed that we get to the end of y before we reach 20. So xy, the string xy together, has to be 20 or less symbols.
Oh yeah.
It can't be more than 20 symbols. So xy together has to be less than or equal to the number of states you have. It can't be more than the number of states you have. Going through the input symbols before our first loop and our first loop. Okay? Read it one more time.
Yeah.
If A is a regular language, then there exists some pumping length such that for any string in the language greater than or equal to that pumping length, that string can be rewritten as x, y, and z, where the xy part is less than or equal to the pumping length. The y part has length at least 1. So we can rewrite s equal to x, y, z satisfying these such that for any natural number you choose, x times y to that natural number z, so x concatenated with y to that natural number z, is still in the language. In other words, x, y, z is in the language, we can pump up that y as much as we want, and it's still in the language. Or we could pump it down to 0, so xz has to be in the language, which is not taking the loop. It's just continuing through here and not going back that way. Make sense? All right, let's go over the proof now. Let A be a regular language. Let M, this is just going to be a DFA. Let M equal to Q sigma delta Q naught F be the DFA, such that the language of M is equal to A. And let P be the size of Q, or the number of states in the machine. So I know A is a regular language, so there has to be some DFA right here that recognizes A. And so now I'm choosing my P to be the number of Q. I need to show that there exists a P. For any language there exists a P. I'm saying here it is. It's a number of states. Let me show that for this P, all this still follows. So far we got our P. It's the number of states in the machine. Okay. Let S be any string in A where the length of S is greater than or equal to P. Now, if your language does not have any such strings, then we're done. It's vacuously true that every string longer than that length can be pumped up, because there are no strings longer than that length. So if your language is just A by itself, and there's your whole language, then yeah, that can't be pumped up, because there are no strings longer than the pumping length for that regular language. Because the pumping length for this language would be P equal to 2. So it's vacuously true if there are no strings greater than the pumping length. We're saying that there exists some length such that any strings in the language longer than that length can be pumped up. Okay. Yes, okay. If no such S, we're done. Everyone good with 2? No?
Can you just say it one more time? Why are we done? Okay.
We're proving that every regular language, if it has long strings, those long strings can be pumped up to even longer strings. What if it doesn't have long strings? Well, its long strings can still be pumped up. All the strings in this language of length 2 or more can be pumped.
Yes. Okay.
There just aren't any. Okay. 3. Okay. So we've got our string S, and so far, what do we know about S? S has length greater than or equal to P, greater than or equal to the number of states in the machine. Good so far? So let Q naught, Q1, dot, 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 Q star be the sequence of states M goes through while reading the first P symbols of S. So S is some string. It has more than P symbols. Up here, our string had 40 symbols, where P was 20. So our string has more than P symbols. Here's a sequence of states it goes through, reading the first P symbols. Possibly lots of repeating states, who knows? Good so far? Now notice, if Q0, Q1, Q2, all the way to Q star are the states that we go through reading 20 symbols, or reading P symbols, how many states did I go through? P plus 1. If I read one symbol, I've gone through 2 states. If I've read 2 symbols, I've gone through 3 states. If I've read P symbols, I've gone through P plus 1 states.
Why are we making P symbols if it's already P is already states?
P is a number of states in our machine. It's just a number.
So it just turns into symbols because it's
So P is a number of states in our machine. So it's just some number, like 10.
Okay.
So what I'm saying here is, if we keep track, so your machine reads 10 symbols. How many states does your machine have to transfer through? 11. So in reading P symbols of our string has at least P symbols. So in reading P symbols of our string, you have to go through at least P plus 1 states. We're calling them Q0, Q1, Q2, Q3, to Q star.
Is there, I mean, just out of curiosity, is there?
No.
Okay.
I just chose Q star to make it weird, to make sure that you're not thinking that this has to do with other sequence of states that we did for like accepting a string. Q star is going to be somewhere in the middle. It's not an accept state.
Wait,
We're just in the middle of our machine somewhere.
You can do epsilon with these
What?
machines. If you have Q star, then you can do
This isn't
epsilon.
the same sense of star. That's
Okay.
what I was wondering.
Q, it's just a label, Q prime.
Yeah.
I'm just calling the state that we end up in. After reading P symbols, what state are you in? Q prime.
Not Q accept.
Yeah, we can name it John, we can name it Phil. It could be an accept state, but not necessarily.
Okay.
It's just a state that we're in after reading P symbols.
It could be an accept state.
It could be. Some random state in the machine. We know nothing about Q prime, except for that is the state that you are in after reading the first P symbols of our string. You're in state Q prime. And the sequence of state, Q0, Q1, Q2, Q3, up to Q prime, has to have P plus 1 states in it. If we read P symbols, there has to be P plus 1 states listed out here. If I wrote out all of them and we counted them up, we'd count up P plus 1. Does that make sense? Okay, so there's P plus 1 states. So then the sequence of states, this sequence of states, then the sequence must have some repeating state, since M only has P states. So if this sequence is a sequence of P plus 1 states, and our machine only has P states, then we must have written some state twice.
At least one state.
It's like if I give you the symbols A, B, and C, and I say, I want you to write out a sequence of A's, B's, and C's, a sequence of 4 A, B's, and C's. I'm guaranteed that you either use A twice, or B twice, or C twice. Same thing. There's only P states in our machine. This is a sequence of P plus 1 states. So we had to write some state twice. And so we're going to call that state Q sub R. So whatever the sequence of states is, I know it has to do something like this. Q1, Q2, eventually we get to some state QR that we get to again later on in our sequence. QR has to show up there twice. Maybe they're the first 2 states. Maybe they're the last 2 states. Maybe this QR is the first state, maybe this QR is the last state. But in our sequence of states, somewhere along the way, we have to hit a Q sub R, and we have to hit it again. Q sub R has to show up there twice. Good? Okay. So then the sequence must have some repeating states, since M has only P states, and we'll call it Q sub 0, Q sub 1, Q sub R for our repeating state. R for repeating. Okay. Now we label. So I found a p such that for any s I have longer than p, I now need to find an x, y, and z satisfying these conditions. So now I'm going to label those. That's the next part. We're coming up with our x, y's, and z's. So I'm going to let x be the portion of s read going from q0 to qr. So x is whatever portion of the string we read going from this state to this state. In our picture here, that was going from this state to here. That's R. Y is going to be the portion of the string going from QR back to QR. So whatever input symbols we read going from here to here, we're going to call Y.
Why are there multiple QRs?
Why are there?
Can there be multiple QRs that are repeated in the loop?
Oh, yeah, there could have been a lot more QRs after that. Yes, we're taking the first two that show up. Or any two that show up, actually. It doesn't have to be the first two.
Okay.
I'm just guaranteed that in reading my first P symbols, there had to be 2 repeating states. There could have been 100 repeating states. There has to be at least 2. Well, there could be 100 with only 2 symbols, but
Couldn't there be one if the loop lives on itself?
there can be many loops in a machine. We're guaranteed that there's at least 1 loop.
Yeah.
So,
one root.
if we're keeping track of our string, it had to loop at least once.
Yeah.
So it has to have some repeating state. QR could show up in here 5 times, but it has to show up at least twice.
Oh yeah, but there can only be one repeating state.
No, there could be many repeating states.
Or yeah, there can be, but there can be. There can be more, but there can be one.
There has to be at least 1. There can be many.
Okay.
So there has to be some loop going from QR to QR.
Good.
There might be many loops in the machine. Just find 1. We're guaranteed that there's at least 1, so we're going to call it this thing.
Okay.
Okay, so we're calling X the portion of the string that we read going from Q0 to the first QR, going from here to here. Maybe label in our picture here. This is Q0, this is QR, and we're looping around back to QR before we go on our merry way to Q accept. Right? Okay. So X is a portion of our string going from Q0 to QR, so from here to our first QR. Y is a portion going from QR to the next QR, so from QR to QR. And then Z is the remainder of our string. So Z goes from QR to some except state. We haven't listed it out yet. But Z is just the rest of the string. And the string was accepted, so Z goes to some except state. Right? Okay, so S is now equal to X, Y, and Z. Now observe that the length of the XY part has to be less than or equal to P. Because P is how far we get when this is getting to P. This is when we read P symbols. And our X was getting to here, and our Y is getting to here. Altogether, X and Y get us this far. So it could have at most gotten us to Q star, which is where we read P symbols. This is the furthest QR could have been, is when we read P symbols. These were all the states we transferred through,
Right.
reading the first P symbols. This state is the state we're in after reading P
It's
symbols.
not the end state. It's not the end
It's not the accept state. That's why oh, oops. This is still prime. It's the same
Yeah.
prime as that. Yeah, sorry.
I made the same mistake you wanted me not to make.
Okay. Right. I'm trying to make it clear this is not an accept state. Could be, but it's not necessarily. This is the state that we're in after reading 20 symbols. Notice that reading our X and reading our Y come before we read all P symbols.
So why'd you say QR to some accept state after the 5? If it's not an accept state.
That's the portion of Z. Forget about Z for a second. Just focus on the XY. I'm trying to make sure that you understand that XY is less than or equal to P. That's the point of putting that prime there. This prime is where you get when you read P symbols. X gets us this far. X and then Y gets us this far. X and then Y could have at most gotten us all the way to Q prime. Couldn't have gotten us further.
Oh, I see.
Q prime is how far we get after P states. So the length of xy can be at most P. It could have been longer than P. It couldn't have gone to some state after Q prime. Our repeating state had to come before or at Q prime. Couldn't have come later. Well, there could be another loop later, don't think that. It's just that we're guaranteed that a loop happens before or at Q prime. We're guaranteed there's a loop before or at Q prime. And so the part before the loop and the part in our loop, the length of those two strings together has to be less than or equal to P. How far we get all the way to Q prime. That make sense? Now what was Z? Z is after this QR to wherever our end state is when we're done reading the whole string. This is just the states for reading the first P symbols. When we finish reading all the string, there's a lot more states that we go through, and we end up in an except state. So that's why Z was a portion of string from this QR to all the states that we go through to finish reading the string.
So this is if the string is longer than the amount of sets that we have.
Right. This only is for let S and A such that the length of S is greater than or equal to P. If no such S exists, then we're already done.
Okay, yeah.
We showed every string longer than that can be pumped. There just weren't any. So yes, we are very much using that fact. Okay, so then we have the part of the string before the loop and the loop taken together have to be less than or equal to P. Since they're before Q prime, and that's before or at Q prime. It could have happened at Q prime because it's less than or equal to P, not less than P. Right? And observe that the length of Y is greater than or equal to 1. Since QR to QR has at least two states. The closest these two QRs could have been is right next to each other, which means you have to read at least one input symbol going from QR to QR. So the length of Y has to be at least 1. Because the closest our repeating states could have been to each other is right next to each other. In which case you have to read at least one input symbol to get from one to the next.
They can't be the same state.
No, because that's not a repeating state.
But if the circle turns on itself.
We're writing the sequence of states that you were in. We're not writing out all the states of the machine. Maybe do something to the side here really quick just to give us a feel. So I'm going to write a really small machine, Q0, Q1, 0 takes us here, 1 takes us here. We'll make that one the except state. Who cares what they do on the other symbols? Our sequence of states could be, if we're looking at the string 1, 0, 1, 0, 1, 0, that has length longer than 2, which is the number of states in here. So when we write out the states for this machine, in reading the first two symbols, so sorry, here's our start state. So we start out Q0, there's our start state.
Yep.
After reading 1, where are we?
Don't know. Dead.
Oh, oops, I meant 0, 1, 0, 1. After reading 0, where are we?
Q1.
And then after reading 1, where are we?
Q0.
So Q0 is the first repeating state. Here's QR and QR. They're the same state, but the closest that they could have been to each other was if I had Q0 coming to itself now on a 1.
Oh, I see what you're saying.
In that case, so now if that happened, then we could have had 1, 1, 0 looking at that string, or just 1, 1, look what happens. Then we would have, well, we'll say 1, 0, then look what happens. Then we have Q0, Q0, Q1. I'm guaranteeing that this machine, any string of length 2 you choose that goes through this machine, is going to have 3 states that it goes through. And so there's going to be a repeat. If you read a length 2 string with this machine, you're going to repeat a state. And the closest that those repeats can be to each other are 1 unit apart. The minimum number of input symbols between the repeat is 1. Here we could get through 2 input symbols before we repeated. Here we got through 1 input symbol before we repeated. So the closest this QR can be to this QR is right next to it, in which case the loop has length 1. Y is the length of our loop, so our loop has to have at least length 1. The smallest loop that we can have is a loop like this. where it just goes to itself. A longer loop is going to here and then back to here. There's a longer loop. And we can build a big machine with a really massive loop.
Yep.
Okay. Perfect. So you get the xy, you get that you understand why x with y, x together with y has to have length less than or equal to p, and why y has to have length at least 1. The loop has to come before we finish reading all p symbols, and the loop has to have at least one symbol in it. So then we come back over here. So then x takes us from q0 to qr, y takes us from qr back to qr, and z takes us from qr to q accept, where q accept is some accept state.
Okay.
So then, notice what happens if we do, I should have written out a concrete example for a second. So now, look at what happens when we do something like x, y cubed, z. Where do we go? Well, x takes us from q0 to qr. The first y takes us from qr to qr. The second y takes us from qr to qr. And then the z takes us from qr to q accept.
There's 3 y's.
Oh, I meant to say it 3 times.
Okay.
But you get the point.
Yep.
So you see how it accepts this string. And so for any natural number you choose, pick one, doesn't matter. I'm guaranteed that x, y to that natural number z, when we express that in terms of the sequence of states it goes through, that is going to go through the state, x takes us from q0 to qr, y takes us from qr to qr I times, as many times as you want.
Yep.
Notice that I can be 0 here, in which case we don't bother with the loop.
Yeah, okay.
And then z takes you from qr to q accept. And by definition, if we can find some sequence of states that your string goes through, then the machine accepts. We found the sequence of states. Therefore, that string is accepted by our machine M. It's pain to get the pumping lemma, but it makes a lot of sense if you can connect it with that intuition of long strings have to loop in my machine. Because your machine has to be finite. It's a finite state machine. So that's the pumping lemma. Not too bad? Now we gotta talk about not the pumping lemma. How do we negate this? Yes, I told you. First thing we were going to show is that regular languages have the pumping property. How are we actually going to use the pumping lemma though? We're going to use it this way. We're going to show something doesn't have the pumping property, and therefore it's not a regular language. And so now you need to understand what it means to not have the pumping property. And so we've got to negate this thing. Now fortunately with some logic, negating isn't too bad. How do you negate? You flip all your quantifiers and negate your last statement that's ultimately leading up to. So all your there exists become for each. All your for each becomes there exists. And we ultimately negate this thing. And so we're going to say x, y to the iz is not in A. So here it is. Not the pumping property. It says that for any pumping length you choose, I can always find a string such that no matter how you split the string up, as long as it satisfies these properties, the x, y is less than or equal to p and the y is greater than or equal to 1, I can find some I such that the I find makes so that the string is not in the language. For any pumping length, there exists some string greater than or equal to p, such that no matter how you break it up, as long as x, y is less than or equal to p and y is greater than or equal to 1, I can find some I such that if you pump y to that I, it's not in the language. That's exactly what we did over here. So over here, I said for any p you give me. Levi chose to give me the p20. But I could have done it for any p you chose. It didn't matter that we chose 20 there. For any p you choose, I can always find a string. The string I chose was 0 to 21 to 20. Not every string I find of length greater than or equal to p can I do it with. There just is going to be some string. I can find some string. Here's a string I found. Of length longer than p. Notice the string I had length longer than 20. Such that no matter how you break up this string, keeping the xy part less than 20, so the xy part has to be in the zeros, I can find a number to pump it up. The number I chose was y equal to the 2, such that the new pumped up string is not in the language. And that's how we show not the pumping property. It's a mouthful. Takes a bit to get used to these quantifiers. Hopefully those of you who have had logic, it's not as bad. But 4 quantifiers is always a beast to work with. Okay, so let's try an example now of actually proving this one that we talked about over here. Okay, and actually proving these things, not that bad, as strange as that is. Understanding the pumping lemma, a lot harder than actually using it. So, a equal to 0 to the m, 1 to the m, where n is any natural number, is not regular. That's what I'm proving. Proving a is not a regular language. Assume by way of contradiction that a is a regular language. Right? I mean, so this leads to some contradiction. If we assume it's a regular language, what do we know? We know that there exists some p, such that for any string longer than p, we can split it up this way, such that the resulting string can be pumped up. So since it's regular, I know that this is the case, and I'm also going to show that the pumping string cannot be pumped up, and that's going to be the contradiction. Therefore, our assumption that the language is regular contradiction, or is false. So assume by way of contradiction that a is a regular language, and so satisfies the pumping lemma, and that p be the pumping length, the p given by the pumping lemma. The pumping lemma guarantees me that there is some p, such that all that's true. So let p be whatever that is. I don't know what it is. But it's going to be the number of states in the machine. Then, for s equal to 0 to the p, 1 to the p, same thing we did over here. I chose s equal to 0 to 21 to 21, p was 20. So, then for s equal to 0 to the p, 1 to the p, I'm guaranteed by the pumping lemma. Remember, the pumping lemma says, as long as your string is longer than length p, you can break it up into x, y, and z, satisfying this condition. So since the pumping lemma has to be satisfied, remember, we're assuming by way of contradiction that this thing is regular, so it satisfies the pumping lemma. And so the pumping lemma tells us that for a string, 0 to the p, 1 to the p, there exists x, y, and z equal to s, such that the x, y part is less than or equal to length p, and the y part is greater than or equal to 1. Right? That's what the pumping lemma gives us. Now, since the length of xy is less than or equal to p, and xy is the first part of the string, and it's less than or equal to length p, what do I know about xy?
It's all zeros.
It's all zeros. My string is p zeros followed by p ones. xy is the first part of my string. Its length is less than or equal to p. So xy has to be completely 0, 0, 0, 0, 0, 0, 0. It's all zeros, right? So since xy is less than or equal to p, I know that y is composed completely of zeros. The loop is nothing but zeros, the y part here. If xy is nothing but zeros, y by itself is obviously nothing but zeros, right? So then, x, y squared z, if I add another y, what did I do?
Added a bunch of zeros.
I added more zeros. At least one more. But I added at least 1 0 if I double the y's, right? So then x, y squared z must now have more zeros than ones. Notice the language that we're talking about is equal zeros and ones. X, y squared z must have more zeros than ones. So x, y squared z is not an a. But x, y squared z is an a by the pumping lemma. Contradiction. So our assumption that this language was regular was false. Proof by contradiction. We assumed it was regular. We showed that led to a contradiction, that it both does and doesn't satisfy the pumping lemma. Therefore, our assumption that it's regular is false. Therefore, A is not regular.
So did we really use the contrapositive?
The contrapositive kind of gives us the outline of the proof, right? Whenever you see a for all, you think you give me, and whenever you see a there it exists, you think I find.
Right.
for any p you give me, I need to find a string such that for any way you break it up, as long as you break it up satisfying these conditions, I can find some I such that this is the case,
Right.
which you'll notice I did here.
Right. Oh, I see that. I was just thinking it's more, proof by contradiction is kind of separate from contrapositive, right? I guess not, it's not a big distinction. I was just wondering.
We're showing that a language both has and doesn't have the property. So we need to understand the property and not the property.
Right.
Okay. And therefore A is not regular. Let's do another one. Try and get a feel for these things. Alright. Let B be the language 1 n squared times. That 2 above the n is an exponent. So it's 1 n squared times. So let's get a feel for this language really quick. What's in here? N can be any natural number. When n is 0, then we're saying let me write out some of the strings here. So we can have n be 0, so that's 1 to the 0 squared. Or we can have 1 to the 1 squared. Or we can have 1 to the 2 squared. Or we can have 1 to the 3 squared. Or we can have 1 to the 4 squared. What's 0 squared?
1. Right? Oh, no, sorry, 0.
0. And so we want 1 0 times, which is just the empty string. Oops, I didn't include the empty string when I enumerated them. I'll point that out when we get to it. But 1 squared now is, and 1 time is 1. 2 squared is 4. So this is 1, 1, 1, 1, 4 times. And this is 1, 1, 1, 1, 5, 6, 7, 8, 9. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc. And that's language we're talking about. All those strings. So the number of ones is a perfect square. The number of ones here, how many ones do we have here? 0. That's 0 squared. The number of ones here, how many do we have? 1. That's 1 squared. The number of ones here, how many do we have? 4. That's 2 squared. 3 squared. 4 squared, etc.
Why is that 1 squared 1, 1, not 2? If it's a 2, if it's 1 squared.
You're talking about this one?
Yeah.
What's 1 squared? Here we're doing math. We shouldn't use ones. A. Let's do that. That was stupid of me. Shouldn't have done ones. Bad idea. Because then it's easy to get confused about where the math symbols are and where we're talking about string. Okay. So now we have A to the 0 squared times, A to the 1 squared times, A to the 2 squared times, A to the 3 squared times, etc. So evaluate 0 squared, that's 0. Write A 0 times, that's the empty string. 1 squared is 1, write A 1 time, that's A. 2 squared is 4, write A 4 times. Does it make sense now?
Yeah.
Okay. Yeah, that was dumb of me to use numbers as my symbols when I'm putting in math and symbols together. So, that on my part. So when we're going through this, wherever we see a 1, we'll replace it with an A. Okay, so B is the strings of A's where the length of the string is a perfect square. 0, 1, 4, 9, 16, 25, 36, etc. are the lengths of the strings. This is not a regular language. We're going to prove it. And you can see how this is suddenly going to become really useful, because it's really hard to think that there's no way to create a DFA that can recognize these things. And yet there's not. Okay, so assume by way of contradiction that B is a regular language, and let P be the pumping length given by the pumping lemma. We're assuming it's a regular language, and so we're assuming it satisfies the pumping lemma. It doesn't. We're assuming it does, that's going to lead to contradiction. Okay, observe that the lengths of the strings in B can be ordered by the first length is 0, then 1, then 4. If we put all the strings in order of length, our first string would have length 0, our second string length 1, our third string length 4, length 9, 16, 25, 36, etc. You with me? And so, if a string has length k squared, then the next string must have length k plus 1 squared. If our string has length 9, or 3 squared, the next string has to have length 4 squared. So if you look at a particular string, and it has length k squared, and we were to order our strings like this, then the next string has to have length k plus 1 squared. If we ordered the strings by length. Make sense? Okay. So now we're going to pick a particular string. The string I'm going to pick is S equal to A to the P squared. P is our pumping length, the number of states in our machine. So I'm saying look at A to the P squared. That's definitely a string in our language, right? So we assume that this thing satisfies the pumping limit. So S definitely has length longer than P. And so there exists X, Y, and Z equal to S, not P, such that the length of the XY part is less than or equal to P, and the length of the Y part is greater than or equal to 1. Good so far? So then, what is the length of the entire string S? P squared. Remember, S is equal to A to the P squared. This is how many times we're doing A. S is also equal to XYZ. XYZ is equal to A to the P squared. So what is the length of XYZ? P squared. If XYZ is A, P squared times, then the length of XYZ is P squared. Okay, so then the length of XYZ, which is the length of our string, is P squared. And notice that if we double the Y's, what is the biggest Y could possibly be? What's the longest the Y part of our string could be?
Can it be as long as we want it to be?
No, because X and Y together can't be longer than
Oh.
X and Y together can't be longer than P, so Y by itself definitely can't be longer than P.
Right.
Does that make sense? So, if XYZ has length P squared, then XYYZ has to be longer than P squared, and it can be at most P squared plus P. If we added another Y, we added at most P symbols. X and Y together is at most P symbols, so Y by itself is at most P symbols. It could be more. So if I add an extra Y in the middle of my string, I added at most P symbols. I couldn't have added more than P symbols.
Right.
Does that make sense? So if the size of my string is P squared, then the size of my string when I pump up Y once is at least P squared, and it's at most P squared plus P. Good? Okay. Now our earlier observation. If one string has length K squared, then the next string must have length K plus 1 squared. So observe that P plus 1 squared is equal to, just do the algebra, P times P is P squared. We get a P times 1 into 1 times P, that gives me 2P, and then 1 times 1 gives me 1. Just doing the algebra there. P plus 1 squared is equal to P squared plus 2P plus 1, which is greater than P squared plus 1. So what do we have? I have X, 2Y, Z. We know that that has length at most, or at least P squared, has to have length of at least P squared, right? And X, Y, Y, Z has length of at most P squared plus P, so it definitely does not have length of P squared plus 2P plus 1. It has length of at most P squared plus P, and so it definitely does not have length of P squared plus 2P plus 1. So X, Y, Y, Z is between P squared and P plus 1 squared. And we already talked about how if one string has length this, your next string has to have length this. this is a string whose length is between both those. And so it can't be in the language. There is no string that has length between 16 and 25, or between 25 and 36, or between 36 and 49. So if there's a string with length p squared, the next string has to have length p plus 1 squared. Here's a string that has a length somewhere in between. And so, this string, and so x, y, y, z is not in the language b. But by the pumping limit, x, y, y, z is in the language. Contradiction. Therefore, our assumption that b is regular was false. Therefore, b is not regular. Make sense? All right, let's do another one. Predence. And this is where it would be very helpful for you to do the homework problems.
Imagine.
Yes. These proofs are pain when you first do them. That's why this class is the hardest class I took.
Is this just homework?
Computation theory wise.
Question you have to prove whether it's regular or not regular.
Yeah, you have to do a bunch of these proofs. I mean, and I've gone over with you guys, what is this, our 8th lecture? What the author goes over in 3 hour-and-a-half lectures. In 3 1-hour-and-a-half lectures.
That's pretty intense.
Yeah, it was a very fast-paced class. So, yeah, this stuff, it's not easy. Takes a lot of time to absorb. And doing homework problems really helps you make sure you understand it. Nothing like struggling with a problem to help you wrap your head around it. Okay, so let's try another one. Should we do that one, or should we just jump to this one? You got energy in you for 2 more, or should we just do 1 more?
Isn't that second one?
This one?
Oh, the second one is just really similar to the first one that we proved was not regular.
This one I'll just do a kind of talk you through it type proof, rather than writing everything out explicitly. And maybe that will help. More informal conversation to help a quick game. So C here is zeros followed by ones, where the number of zeros we have is more than the number of ones. So this is one string in there. Here's another string in there. Some number of zeros followed by some number of ones, where the number of ones is less than the number of zeros. So we have I zeros followed by j ones, where I is a number bigger than j. And it's implied that those are both natural numbers.
So every string in there has to have at least 1 0.
Every string in there has to have at least 1 0. This is the smallest string in there. 0. Second smallest string in there is 0, 1. Oh no, we did have 0, 0. That works too. Good? That's the language. We're going to prove it's not regular. Okay, how are we going to prove it's not regular? Once again, Levi goes home, he builds a machine, he's convinced he's got the machine, we show him he's wrong. He won't learn his lesson. He keeps trying to prove these non-regular languages are regular.
Sounds about right.
So first thing we ask him is, how many states in your machine? He tells us p. So we say, okay, consider this string. S is equal to 0 to the p plus 1, 1 to the p. Right? Then we say, we can also write S equal to x, y, z, where this xy part is completely zeros. Because xy has length less than p.
Yes.
Right? So if we rewrite his string as x, y, z, then the xy part is definitely just zeros.
Or could it be also nothing? If your string was just
Y has to have length at least 1. Remember, p is how many states are in your machine. It's not just any string that your machine accepts. So if your machine had 29 states, you can't use the string just 0.
Oh,
Make sense?
yeah.
Okay. And we're not saying that for any string with more than that length we can do this. We're saying that for any number you give me, any p you give me, I can find at least one string whose length is longer. So you don't get to restrict the string I choose. And there might be strings I choose with length greater than p that it happens you can pump them up. Because maybe I'm just stupid in my choice. Here I was smart in my choice. Okay, so I say consider this string. And I say for this string there has to be some way to break it up. So says the pumping limit. You say you have the machine to do it. That means your machine has a pumping limit. So you have to be able to break it up so that x, y are completely contained in the zeros. Right? And so now consider the string x, y to the 0, z. By the pumping limit, you should accept this string where we don't go on the loop. Skipping the loop is a valid option. But x, y, z, how many zeros does that have? This is x, y, 1, z. In case you guys are confused, x, y, 0, z is the same thing as x, z. And we just don't take the loop at all. Right? Okay, so y was contained in the zeros. Right? Y has length at least 1. If I get rid of the y, how many zeros did we get rid of?
At least one.
At least 1.
Well, x, y together couldn't be more than p,
X, y together can't be more than p.
but it can be p plus 1.
No. Our string has p plus 1 zeros, followed by p1s.
Oh, so you just proved it wrong.
Not yet.
But it can't more than p.
First, we asked him, how many states? He said p.
Zeros, yeah.
He said 20. I said, consider the string 0 21 times, followed by p 20 times.
Okay.
I could have just as easily done this, just to make sure things are perfectly clear. Assuming p is a number greater than 1. It's dangerous because now we have to be careful and assume that every machine has to have at least one state. I think we're good. I think this is valid. Okay, so we could have also chose this string.
That can't be valid. Oh, yes, it can. Okay, we're good. All right.
Because p has to be at least 1, and get rid of all the 1s, that's fine. Okay, so 0 to the p, 1 to the p minus 1. So then I say this xy part, since its length has to be less than or equal to p, then the xy part is nothing but zeros. And so the y part is nothing but zeros. And so when I get rid of the y part, I got rid of at least 1 0. So the biggest this string could possibly be now is 0 to the p minus 1, 1 to the p minus 1, which is not in our language C. C has to have more zeros than 1s. It can't have the same number. I just made it have the same number. So the language isn't regular. There's a more informal proof.
You were saying before that x, z cannot be greater than p. But
I'm not sure if I said something weird. The length of xy, did I say z?
it was a while ago, but yeah,
I meant xy. The length of xy is less than or equal to p. We know nothing about the length of z.
Right, okay.
Well, we can infer from that information. Okay, so there's the idea on how you do that proof. So let's do one more now where we can be a little bit clever. Alright, so W, it's a set of all W where W has an equal number of zeros and ones. W is a binary string. So it's this one works. That's in our language. Because it has an even number of zeros and ones. All right, how can we do that one? Let's call this language something. What should we name it? D. D is equal to that. We'll say D is equal to that language. We assume by way of contradiction that D is regular. So
You would show,
assume by way of contradiction D equals a regular language. All right, 2.
your loop. No, that doesn't make sense.
D is equal to 0 star 1 star. I don't know where I had an extra line on that. star, 1 star, intersected with
Isn't it just 0 union
Oh, no.
1 star?
other way. 0 to the n, 1 to the n, is equal to d intersected with 0 star, 1 star. This is all the strings who have a bunch of zeros followed by a bunch of ones. This is all the strings who have the same number of zeros and ones. This is the same number of zeros followed by the same number of ones. So if I ask you to take all the strings that are some number of zeros followed by some number of ones, and we also require that they have the same many zeros as ones, then you're left with the same number of zeros followed by the same number of ones. You see that? Good? Okay. So, what do we know about regular languages? They're closed under,
Regular expressions.
they're closed under intersection. So if this is a regular language, we know that this is for sure a regular language. And so a regular language intersected with a regular language is regular. So then this is regular. But we already know that's not regular. So this can't be regular. Regular languages are closed under intersection. We've already proved that. If D is regular, this is for sure regular. That's just a regular expression, right? We're all good that this is for sure regular. If D were also regular, then their intersection has to be regular.
But it's not.
But this isn't regular. We already proved that in one of these.
So D isn't.
So D can't be regular. Because if it were, this is regular. But we know that's not. Make sense? So we don't always have to use a pumping lemma every time we prove something. Our closure properties are also extremely useful for classifying languages. Good? Alright, we'll call it there. Pumping lemma is pretty exhausting. So we'll end it there. Remember, no class next week. We'll have class normal the week after that. I don't know if you were here when I said that. Okay. And hopefully everyone else can watch lecture.